Hello, everybody. My name is Mauro Semarelli, and in this video, I want to discuss and go over what is multi-path TCP. So when we think of a network, right? We think of many different protocols that help provide a means to transmit data from a source to a destination device. There are many issues that are out of our control in each network. Whether it's an oversubscribed link or equipment malfunction, typically all users want seamless internet reconnections during network outages. The first question we ask ourselves is how can we make our connection faster and most importantly, resilient? The truth, the truth is there are very slim options when you have only one single connection to a device. However, the desire to add a second or even a third connection and aggregate them into one logical circuit is an exciting feature that is provided by a new and rapidly growing protocol called multipath TCP. So, what is multipath TCP? Um, multipath TCP is an extension of the TCP protocol, and it was designed in 2008. And since its inception, RFC 6024 was published in 2013, and this helped put the protocol on the network map. What MPTCP provides is better availability due to the efficiency to use multiple interfaces to establish connections. So to further understand the protocol, we have to look at the limitations of TCP, right? On this demonstration here, we have internet provider A, which is a broadband provider for a residential home. We also have ISPB, which is a 5G LTE data mobile provider. Okay, so on the left we have user A and C that are using traditional TCP flows to connect to a given server. As we all know, TCP does not support multi-homing nor mobility very well. So in the event of a upstream failure, the connection socket will time out and pretty much stall the session where a refresh is required. Traditionally, when you think of TCP, it was fundamentally designed to use TCP flows on point-to-point connections. So when we compare this to MPTCP, right? Let's say we have a smartphone user B that's depicted here on our illustration that is connected to a wireless modem. Um, Essentially, he's using a source IP that's provided by ISPA. The smartphone is also connected to a 5G LTE network provider, and he's using a different source IP. Okay, so let's say you are connected during a video stream and you happen to walk outside. You would expect the connection to drop due to falling out of Wi-Fi coverage area. So the Wi-Fi connection now is gone, but the smartphone subsequently reconnects to the LTE network using a different source IP seamlessly without experiencing any type of delays or any types of connection drop. So this is due to the nature of MPTCP, which allows a device to use multi-homing simultaneously. So before we proceed, we need to understand how multi-path TCP operates. So the protocol uses a concept what's called inverse multiplexing, as depicted on this figure. As you can see here, it breaks a data stream into smaller streams depending on the amount of circuits that are being utilized. Then it aggregates them at each endpoint. What this means is that we can have many media connections. Some could be fast, some could be slow. The protocol essentially doesn't care. It will aggregate them back into one fast logical circuit. When we look at the MPTCP datagram, essentially it's comprised of an application layer that can be pretty much any HTTP traffic streams. These are encapsulated with the transport layer. And when a user opens up a TCP connection, the streams will automatically and transparently pretty much break down into many substreams as depicted here on the network layer. In this figure, we can see that there's three substreams, one stream for every network interface that you may have participating on the aggregate bundle. Now, compared to TCP, which is the incumbent protocol, we have a limitation of only a single IP, which pretty much is just one single path flow design. So multipath essentially was developed to solve one big problem. And that is the roaming problem due to the capability of combining different connections. The advantage of MPTCP is that it allows users to exploit what's called path diversity. So in the event of one connection, right, one connection fails or becomes slow due to oversubscription, multi-path TCP will essentially direct more traffic down that path that is more optimal. This is done by calculating best ping time and validating latency optimization. So our presentation takes us to our proof of concept, which allowed me to create a network topology in a private lab to test MPTCP on Cisco ASA security appliance firewalls. On this illustration here, we see a network with ASA1 and ASA2 here in red. Now, ASA2 will provide internet access to all internal LANs and simulate carrier A and B using MPTCP protocol interfacing ASA1. This segment here of the network was used to test the MPTCP redundancy by simulating carrier failover while connecting to a server on the internet. The next network segment, which is comprised of ASA1 firewall, essentially provides internal LAN layer 3 using the DHCP server option. As you can see here, we have a trunk port. It's pretty much a port channel uplink to switch 1, and it's broadcasting VLAN 100 for management, 200 for user data, and 500 for Wi-Fi. The ASA essentially, as mentioned, will provide layer 3. It's a layer 3 gateway, and what it's used for is to pretty much push ingress and egress internet traffic outbound and inbound. Our next network segment task takes us to the access layer, where, as you can see here, one trunk port will be configured to interface the Linksys wireless AP for wireless access. Part of our test will have the Linux system connect via Wi-Fi and LAN simultaneously using the protocol MPTCP kernel that's installed on the Linux system. So our focal point of the performance of MPTCP on the test on the firewall was contingent on this configuration here, which is defined in 4 steps per the Cisco documentation. The first step here, we define the policy option, which is 30. And essentially what we've done first is we enabled the policy option, and then we went ahead and called it my MPTCP. The second step, we defined a class map, which is used as a catch-all. It catches all types of traffic that need to traverse the appliance aside from our MPTCP traffic. The third step, it pretty much compiles both the class map and the MPTCP policy map and ensures that both are allowed and working properly. And then our fourth step enables the MPTC protocol globally on all interfaces. What this means is that any active interface will essentially participate using MPTCP. So there are 3 test scenarios. As you can see here, MPTCP should be in effect creating multiple subflows. Our focal point will be to disable one of the carrier interfaces between ASA1 and 2 and validate the behavior of the connection. Essentially, we broke this down into 3 hierarchy, and in each hierarchy, we have some type of redundancy. And the goal was for us to test and see how the video streams behave while we're simulating the outages. So on the first test scenario, okay, what we've done here is we validated traffic. The traffic is working per the design, right, and traversing carrier A, as you can see here on this illustration, on both ASA2 and ASA1. Okay. Now, for sake of testing, I have a connection to my NAS Synology server that sits on the untrusted edge, and I'm streaming one of my favorite movies called Saving Private Ryan. So the next step would be to disable gig one, which depicts carrier A, and as listed here on this illustration. Um, Once we do this, what we want to do is we want to validate the behavior of the connection. Okay. So once this was done, Um, as we can see here, traffic essentially shifted over to carrier B, okay, as planned. However, the connection to my NAS stalled for about 15 seconds. As you can see here, we have the buffer. So what this means is that MPTCP did not work as intended. We also obtained packet captures on the ASA, and we saw pretty much no MPTCP packets present. So this test was unsuccessful. My thoughts are due to the MPTCP essentially being a new developing technology. This may require proper firmware patches on the Cisco firewalls to support protocols and help aggregate all participating interfaces. My second theory is the Cisco ASA firewall by default supports two types of failover. One is regular, and the other one is stateful. When a regular failover occurs, all connections typically drop on the firewall, and users need to reestablish their sessions on the alternative link. It appears we actually simulated a regular failover, and it used the TCP protocol, which follows the single path flow design default design. Another important thing that we also have to consider is that the Cisco ASA's models are used are 5510 and 5515X. Although not old, may have software limitations and perhaps they don't support MPTCP as of yet. So further research will need to be done and on newer appliances. On test scenario number two, I performed a failover test on the Ether channel that combined two physical links from switch 1 to ASA 1. So what we've done here is we disabled port 47 on the switch, as depicted here on this image, and we validated the video stream, and we noticed that there was no connection failure. Now, this is normal due to the behavior of the port channel technology. Essentially, it aggregates multiple physical interfaces into one logical interface, and it increases the throughput between the two endpoints. So our last test was performed on the access layer, okay, and it was done at the PC level. So on this illustration here, we can clearly see that we have both simultaneous connections that are up and working. One is to the LAN and one is to the Wi-Fi. So the goal was pretty much to disable the LAN connection. Okay. And on this demonstration here, we went ahead and we disabled port 2 and we seamlessly forced traffic to the Wi-Fi with no video stream interruptions. On this illustration, we could clearly see that the LAN connection failed while Wi-Fi pretty much remained operational and the video stream were not compromised. Our video streams, our Wireshark captures obtained also show MPTCP are present and in full effect and operating as expected. So in today's video, we learned what MPTCP is. It is a protocol that can aggregate multiple available connections into one logical. The way it works is by using path diversity, calculating best ping time, and validating latency on each circuit to push traffic on the best optimal path. We also created three test scenarios while using MPTCP. We performed link failure on the ASA network segment and validated data flows, and the test results were unsuccessful. Perhaps the new Cisco ASA appliances are MPTCP ready with the proper make, model, and software. While using MPTCP, we also performed link failure on switch 1 port channel interfacing ASA 1, and validation and testing were successful. Lastly, we also performed link failure on the Linux machine and forced traffic to the Wi-Fi, and validations and testing were successful. So, in conclusion, I feel that more work needs to be extended on this protocol. The work really needs to support more capable MTCP software on all different types of platforms. This would help the protocol pretty much gain popularity due to its automatic handling of connections and bandwidth optimization. From a user perspective, this is good, right? This is exactly what consumers want to pay for. They want to pay for that redundancy. So this would make MPTCP a good and viable solution for both personal and business network architectural solutions. So I hope you enjoyed this video, and I want to thank you for watching.